So I've been in a professional full stack software development role for a little over a year now. And lately, as I've become more comfortable in the languages I work with, I've begun to try and turn my attention to optimizing and making more performant the things I've already built. This led me down a rabbit hole, including some YouTube videos that I'll post here. And professionally, I work with Python for the most part because it makes the most sense for my use cases. And anyone who's done a fair amount of software development knows that it's about as abstracted away from the operating system and the hardware as a language can be. And I've only recently begun to dip my toes in the Golang waters because it seems that if you can work in any language of your choice, at least one of them should be a compiled language, if only to better understand how the code interacts with hardware, memory management, caches, and all that other stuff. And this seems like a must for any self-respecting dev who wants to deeply understand things. So rather than trying to tune a script on my pretty powerful work computer or my relatively fast home computer or one of my 1-liter cluster computers, I thought it would be more interesting to try and find as much performance and optimization as possible with true hardware limitations, as opposed to pretending software and hardware limitations exist. I guess we can just call it trial by C++ fire. So I bought a Raspberry Pi Zero, which I think is the smallest single board computer they make that has Wi-Fi, which I needed to SSH into it to make my life a little bit easier for all of this. And I just added the heatsink here. So this has a 4-core, 1 gigahertz CPU, 512 megs of RAM, and less than a meg of L1 cache. So the main question I wanted to answer was how much performance I could get out of this thing. And the secondary consideration, which was not nearly as important as the first, is whether or not I could store any of the data that I'm finding or using. For anyone who watched my video on my Beowulf cluster, will know that I have a thing for prime numbers and searching for prime numbers as a pretty good benchmarking test for relative performance. I guess we can blame my math degree on that. So I ordered this, and while I waited for Jeffrey Bezos to deliver it, I cracked open my ancient T480 ThinkPad and had GPT write a C++ script on a single core to find primes. And then I left it in my office, said goodnight, and let it run all night. But being the impatient person that I am, when I got home, I had GPT write a Python script with the same algorithm, using 3 cores on my home computer. And after 30 minutes, it found 666 million primes, so about 22 million a minute. And it took up 7.5 gigs of an uncompressed text file where each line is a prime, and only houses a single prime number that the algorithm found. So, not knowing a lot about number theory, especially with respect to primes and their theorems and whatnot, I kind of assumed that primes became less dense rather quickly, but this is apparently not the case. The internet says prime density shrinks at about 1 over the natural log of n, where n is the average value in the range you're looking at. So that kind of explains the linearity of primes found per unit time. And ChatGPT said that based on how quickly the algorithm was finding it, I would have to run it for nearly a year in order to see any real curvature in this graph. As for the file size per unit time, which is also interestingly quite linear, the linearity can be explained by the fact that while prime numbers very slowly become less common, each new prime number that you find is going to be bigger than the previous. So you're going to find them less and less frequently, but they're going to take up about the same amount of space because they're getting increasingly larger, which is kind of an interesting cancellation. So all that to say, storing the primes didn't really look like it was going to be feasible. So even if it worked at 1/10 the search speed of that initial Python script, that would have been 1,400 megabytes an hour, 35 gigs a day. That would add up pretty quickly, so that was kind of out of the window. So there was a lot of stuff to consider. As far as optimization goes, running it headless seemed pretty obvious. And rather than having constant outputs to the terminal, which do take up CPU cycles, even if it's not very many, is still, preferable to not lose any CPU cycles if possible. And before I had really was storing all the primes, I thought about running it off of a battery backup of some kind to avoid brownouts and like power fluctuations and things like this, which I thought, a single board computer like this might be rather susceptible to. And then I did the math, and apparently running this for a week straight would have required basically a $500 power bank, so that was out of the window too. And at first I was going to settle for plugging it into my APC, which I have my home server, which is just a 1-liter PC, and my router plugged into, and then I was like, well, I have to have it attached to my monitor, at least for setup, because the keyboard is going to have to be Bluetooth, because this only has micro USB, and I didn't have an adapter, and I didn't want to wait another week for Jeffrey Bezos to order that, because I don't know how to plan ahead. But otherwise, using C++ seemed like pretty much a given. Assembly is too much for me. I could use a stripped down version of Python, but that seemed like shooting yourself in the knee right before a sprint. And I wanted a good reason to start dipping my toes into C++, because for, whatever reason, the more I fiddle with Go, the more I kind of wish I just went with C++ to begin with, but that's a whole other thing. So I decided to keep everything stock. No overclocking, no other fiddly stuff, just to see where we could get without tweaking those types of things. Beyond that, there's more trade-offs. Do I want no record keeping at all? Do I want it to output every 100th prime, every 1,000th prime, the last prime that it finds? So to start with, I needed to decide on an algorithm, and I decided to go with a segmented sieve of Eratosthenes, which I'm probably mispronouncing, but you can Google it, or here it is. A sieve works basically, is a whole lot faster than brute forcing something, searching, for every number you want to test, searching from 2 to the square root of that number is, wildly computationally intensive. A sieve basically starts at the bottom of your range, whatever range that is. Once it finds a prime, it also eliminates all the multiples of that prime so that they're not unnecessarily checked later on. Because if you find a prime and then you find a multiple of that prime, well, obviously the multiple of that prime is not going to be a prime as well, because it's going to be divisible by the prime you just found. Having a segmented sieve breaks it down a little further. So for a set of numbers like 2 to n, you start at 2, 2 is prime, you add that to your list of your primes, and they'll eliminate all of its multiples like I just said. And your next number is 3, 3 is prime, add it to the prime list, add its multiples, and then you go on and on and on, except you only work with one segment of numbers that you're working with at a time. Especially, this matters more if you're dealing with a very large set of numbers. If I want to test all numbers for primality from 1 to a billion, well, on something like this, I can't hold all of that in cache. Maybe not even in RAM. So you have to deal with a segment of it at a time. And it's kind of funny, going back a little bit, it's kind of funny that I even considered running this indefinitely, because if you think about it for more than 5 seconds, you realize that no matter what kind of computer you're working with, eventually you're going to run out of RAM. Because even if you make the segment in your sieve smaller and smaller such that you're only testing one number at a time, well, at a certain point that single number isn't going to fit in RAM either. No matter how much RAM you have. So if I were to run my development computer with 32 gigs of RAM indefinitely, I don't know, maybe a couple days to a week or two before the RAM runs out and it can't process numbers that big. So it was silly. It was a fun thought for about 3 seconds. So I'll give you a little bit of dessert first. The generic sieve, not segmented, just a generic sieve on the aforementioned development computer that I do most of my work on, found 54 million primes in 10 seconds. That's not optimized at all beyond just being a generic sieve. There's no RAM optimizations, there's no utilization of built-in hardware functionality, CPU functionality, stuff like that. At the end of the day, after going back and forth with ChatGPT and Claude for several days, I was able to squeak out 7 million primes, 7.4 million primes a second on this little thing, which was kind of shocking to me, but I'm also incredibly ignorant. When it comes to hardware capabilities, when we're talking about low-level compiled programming, it really makes things like Python look laughable. Perhaps that's what everyone is kind of implying when they say Python's a joke with respect to compiled languages. But anyhow, I started out with a half dozen varieties of a sieve. Started out with unsegmented, segmented, incorporating various types of optimizations. And it was kind of a pain in the neck because, like I said, I did have to use a couple LLMs to help me with these scripts because I don't work with C++ at all. I barely know Go, and this project is just like a couple day project, doesn't really justify sinking time into learning C++ just for this in that short period of a time. I just don't have that kind of spare time. And that wasn't the point of the project anyways. I do plan on learning C++, but that's going to be on a much longer time scale, obviously. But having all these variations of a sieve and trying to troubleshoot them and tune them, work on them on my development computer, SCP them to the Pi, compile them, run them, and became a pain in the neck. So I just stuck with one of them that I thought would be the most promising, and I iterated off of that one between my development computer and then moving it back and forth to compile and run and all this other stuff. So don't give me too hard of a time when you look at the code and you're like, wow, this GPT definitely wrote this. Yeah, it did, with a whole lot of feedback from me, but yes, it wrote it. Still a decent learning experience, just not within the confines of learning C++. So I'll talk about all the individual optimizations in a second, but right now I want to talk about data validation. I don't know C++ well enough to inspect the code directly. My low IQ solution was to make another version of the script, which searched until it found 250,000 primes, saved them all to a text file on the Pi, stop searching for new ones, and then turn around and check if each of those numbers is in fact prime. So after I found the 74 million, I came up with this one, and all of them passed. All of them were definitely prime. So worst case, there are some primes that I didn't find, but there were no false positives, which is cool. I was pleasantly surprised by that, which makes, kind of makes me wonder what kind of insane performance you can get out of a full-blown desktop. That's a video for another day, I guess, but I mean, the concept is still basically the same. So let's talk a little bit about the optimizations. So we already talked about using a segmented sieve and what a sieve is, and sieve. I go back and forth all the time, I apologize. We talked about what a sieve is and what it meant to segment it, and we made the segment small enough to fit in just the L1 cache, which isn't very big, but it has a much smaller delay with respect to CPU cycles when it comes to accessing it, right? Like, this is a standard thing across CPUs. L1 may take only 1 cycle, L2 cache may take 5, L3 cache might take 100 cycles. And when you're trying to squeeze out every single drop of performance, that is a really big optimization to make, keeping things in L1 cache whenever possible. And then obviously in the sieve, we skipped over every even number. That automatically cuts out half of them. That's one of the larger optimizations you can make and very easy to implement. And since this is multi-core, we were able to do some multi-threading, which means we're splitting up a job or a task across threads while trying to minimize as much as possible the kind of administrative and orchestrating overhead the overhead that comes with trying to orchestrate multi-threading, because you can't just wham bam, thank you ma'am, implement multi-threading and not expect it to actually cause slowdowns if it's not done correctly or done well. So you have to be careful about doing it. It's not just adding nitrous to your car and it's just gonna go faster even if your implementation is jank. So that's a big one, especially having 4 cores. I believe I only ran it on 3 so that I didn't crash it. But you can check the script if you like. It's in the repo. It's public. Beyond multi-threading, we also did bit packing, which was a completely new thing to me and very interesting. When we're talking about the segments in this segmented sieve, and this is really only an optimization with respect to this kind of problem of hardware limitation. If we didn't have the limitations of RAM and L1 cache, we would not have done this. So this is kind of something where you have to like take 2 steps forward, but you get to take 2 steps back, but you get to take 5 steps forward, and you're only netting 3, but you are netting positive, you know what I mean? So when it comes to bit packing and this segment that we talked about, and for each number in that segment, we map it to just a single bit, not even a byte, a single bit, a 1 or a 0. And we can kind of cheat and sort of lick our own elbow. And instead of working directly with the integers themselves, which are taking up a whole byte, we can work with the individual bits themselves, especially when it comes to marking one as prime or composite, 1 or 0. And that means you're using, 1/8 as much memory for that, which means you can work with a much larger segment, which means you can do more segments per unit time, etc. And then once we've done all this magic, then we can reverse map from that bit back to the integer itself, and we're able to sidestep some of the work, some of the memory requirements, I should say. And then we did what's called pop counting. Pop counting means we can sort of lump actions together. In this case, we can look at that segment of bits, and we can mark as many as we want as prime in a single instruction, as opposed to going to one by one. This one's prime, this one's composite, this one's prime, this one's prime. We can mark all the primes as prime in one operation. And that's a feature at the hardware level. That's most of the hardware considerations. As far as the command to compile, one of the things we did was enable SIMD or SIMD processes, so it's single instruction, multiple data. Like in our mapping from the integers to the bits, we can clear all the bits at once rather than one by one, which is really nice. We use the O3 flag, which means we can optimize the code for vectorization and predictive branching. And we got rid of some of the C++ overhead that was unnecessary. Beyond all of that, for fun, I decided to overclock it. So it comes out of the box at 1 gigahertz flat. I tried 1.3, and that worked. And I tried 1.35, that worked. Tried 1.4, that immediately crashed. So I reverted back to 1.35. And then I ran the same script again, and instead of 74 million, it found 90 million primes in 10 seconds. And there's no reason for me to go back and validate that because the algorithm hasn't changed. It's not going to get more unreliable with speed. So 74 to 90 is about 20%, which is, I would say it's a pretty big deal. That's 9 million primes a second. Which, I'm a hardware normie, so that's incredibly impressive to me. So that more or less concludes the things that I learned and the project itself. I just wanted, like I said at the outset, I wanted to know what goes into optimizing a script or software for not just really simple hardware, but a very particular set of hardware, right? Like, we created the segments and everything else with these particular parameters in mind with respect to the exact amount of RAM, the exact amount of L1 cache, L2 cache, etc. And I had a lot of fun. I don't know what I'm going to do with this now. I don't have anything in mind. I have other projects that were waiting on this one, to complete before I could start. I got a Model 4 waiting for me to build a home security camera from scratch because I don't trust Ring with my data. But anyway, I had a lot of fun. Hopefully you found this video at least entertaining or interesting, if not downright educational. That would be pretty sweet. And if you think this kind of benchmarking performance stuff is interesting, you may find interest in my video about building a Beowulf cluster and using Go to find primes. And if I refactored all of that for C++, this, I don't know, we would have so many zeros it'd be an absurdity. But anyhow, thanks for watching. We'll see you next time.